But while we're waiting for more people to come on in, we can get started with preliminaries. And I suppose first on the preliminaries, ladies and gentlemen, how many of you actually do have iClickers? No. For how many of you will, right, or are actually able to participate in this attempt to add interactivity to the lecture and make it a little bit less lecture-ish? I'm hoping for a number above 100. No, doesn't look like we're going to make it. Okay. Too bad. Yay. Okay. It helps us, it helps me gain a sense of where the class is. And I think it also helps you if you have and if you use your iClickers. Simply because it helps you pay more attention. It kind of knocks you out of the kind of zoning out kind of state of mind. I at least am one of those parents who has thought that it's been a lot better that my children and the people in their cohort have been using computers in the same context when my cohort was simply watching TV. That watching TV is an incredibly passive and zoning out medium, while whatever you're doing on the computer, you're reacting. Even if you're just playing Halo, let alone medieval Total War, let alone other things. There's a certain amount of interaction and response there that I think is very good for the brain, and that applies to you people as well, even though your brains are now almost entirely formed. So encourage you to get them, because there are real extra credit points associated. We continue to wage our war against the waitlist, and so I want to figure out what the current state is of people coming who are either planning on dropping or who are still on the wait list, who haven't managed to get themselves off of the wait list yet. So if you could go to your iClickers and if you could start clicking away. Okay, that's going to be about our maximum. What are we doing? Okay, so we still got 9 people who are here, but want to take this class if they can get on the wait list. And the last I looked, we still had 12 seats. So I suspect your problem now is you're trying to get into a section that's full. So try to get into some other section that isn't full, and then go and beg Dariush for permission to attend a section you can attend, even though you actually can't make the section that the bureaucracy thinks that you're enrolled in. And hopefully everything will work out. Hopefully. And here we were as of yesterday lunch, right? 14 available seats, 20 on the wait list. That should be manageable, especially because one of the consequences of having a university that's not offering enough classes in large enough rooms is that once you're into a class, that basically only death can force you to drop it before the absolute last minute. That is, everyone knows that if they're in a class and if they drop it, they won't be able to get back in with high probability. So even if there's only a 5% chance that you want to take a class, you're going to stay in there until the last drop deadline and only then drop it, which makes it extremely difficult for those of us up here to figure out how many of the people occupying seats in the class actually want to take it. If this were the economics of transition, or this were comparative economic systems, we'd then go into a song and dance about how this is one of the inevitable defects of central planning systems. That it's impossible to set them up in such a way that people have incentives to truthfully reveal what they really want to do and what is going on. And this is one of the great excellences of markets. That is, if you don't want to buy it, you don't buy it. If you don't want to sell it at the current market price, you don't sell it. Market systems are very good at getting people to truthfully reveal what they think and what they want in a way that other more bureaucratized, more centrally planning systems are not. And we're dealing with that. And I think that's probably the reason that the waitlist hasn't cleared completely by now, but we'll see. We also say that we have a bunch of Haas majors in this course. And let me warn you again, this is really probably not the right course for you. That is, it doesn't teach you enough about a bunch of things that you ought to learn if you're a Haas major taking a macroeconomics course. It doesn't teach you enough about financial markets in the business cycle. It doesn't teach you about risk return and how they vary over the business cycle. It doesn't teach you about how the cost of capital shifts over the business cycle. We aren't going to do anything about markups and margins in the business cycle, unless April comes around and I happen to be working on a markups paper, which I might be. It don't teach enough about demand, productivity, and costs and how the business cycle affects firms' production decisions. Those are all things that Haas majors ought to know. We don't do that. We're going to be doing more political economy and public policy-ish stuff with occasional excursions into sociology. You'd be better served in the counterpart Haas course. Now, I realize that schedules are complicated and that's not possible, but I really don't think this is the right place or the best place for you to be. But then I'm also an economist. And as economists, we know that people can't always do the first best, that everyone is trying to optimize under constraints. And economists also strongly believe in individual autonomy, on the grounds that you are probably better judges of your own self-interest than I am, at least unless I want to peek deeply into the situation. But at least think about it. Sections, we now have 3 Monday, 2 Wednesday, and 1 Thursday section, correct? And are these all in the right spaces after we finished moving everything around? I think they are. Here's where our sections are. And problem set 1, as I said, it was up on the web. It's due on Thursday at the start of lecture. And as I said last time, it's a combination listen to lecture and data scavenger hunt problem set. It ought to be easy to do. Now a little recall from last time, that I tried to pound one number into your heads about the magnitude of economic growth that we've seen since the invention of agriculture, since the days 10,000 years ago when we really stopped being hunters and gatherers, settled down, started farming and herding, and thus truly acquired the ability to build up lots of physical capital. We could build houses that we would then use more or less constantly, and also lots more knowledge capital, it being a lot easier to remember things if you aren't moving around. Okay, and we're now up at 62% at what I think the right answer is. But, you know, the people who want to say it's very difficult to compare what our standards of living are to those of, say, Gilgamesh, king of Uruk in 5000 BC, there's a strong point. To that. Now back on to what we're going to be talking about today, which is the long-run evolution of important macroeconomic indicators. And what do you think we're going to talk about today? What do you think the most important macroeconomic indicator is going to be? Which of these am I going to start with? These are all things that are among the list of 6 key macroeconomic quantities in the textbook. Which of these do you think is the most? Okay. Yep, real GDP. Real GDP is it. It's the thing we look at most. If there's one single economic statistic that we want you to remember, it's going to be real GDP. It's our single consensus most used overall measure of economic activity. And in the 3rd quarter of 2007, real GDP was $14.1799 trillion at an annual rate here in the United States. Composed of consumption spending, investment spending by businesses, including an involuntary increase in inventories that businesses really didn't want to see in the third quarter of 2007, and that then led them to fire people because they were producing a little bit more than they could sell, government purchases, and then this huge honking negative net exports term because we were spending a lot more than we were kind of producing in the United States in the third quarter of 2007. We're doing the same today. And this GDP is our best single measure of the circular flow of economic activity. The process by which households buy things from businesses, and as they spend money, they get their cash over to businesses, and the businesses then use the cash that households have spent in order to pay their workers, in order to pay their material suppliers, in order to pay for rent and for capital and for entrepreneurship and for profits. And that flow of incomes back to households then gets the households back the incomes they then need to go and buy their next round of purchases. And the whole economy holds together in one gigantic circular flow. Back in 1803, back at the start of the modern age, there were a number of people who were worried that this circular flow could break down. That we were no longer in a world in which people largely made what their own households consumed and traded a little bit. Instead, pretty much everything was being traded. Indeed, maybe 5% of what I consume is something that I make myself, and most of that is just scrambling eggs, I must say, and other related things. The extraordinary divergence between the 5% of the stuff I consume that I make and the perhaps 80% of the stuff they consumed that they made when you go back only about 6 generations in my ancestor tree is an absolutely amazing statement of the economic changes of the past 3 centuries. Back in 1803, people were worried that the system might break down. And economist Jean-Baptiste Say, in refuge from the rather sharp guillotine-esque tenor of French politics, in refuge in the countryside, said, you don't have to worry about that. Since nobody makes unless you plan to use or sell, and nobody sells unless you plan to buy, total planned sales must be equal to total planned spending. There can be excess supply of some particular commodities but if there is, there's excess demand for others, and the people who are making the commodities that are in excess supply then have a big incentive to hot-foot it over to the industries that are expanding where there's excess demand, get themselves retrained, and start making something that consumers actually want to buy. And so we don't have to worry about the whole system not holding together. Jean-Baptiste Say's claim sounds a little hollow today when you look outside, especially if you're a senior contemplating a job search right now in a U.S. economy where the unemployment rate is still close to 10%. And indeed, John Stuart Mill, a generation after 1803, pointed out the potential problem with Say's law, that people don't just buy currently produced goods and services with their incomes, they buy and sell financial assets as well. And you can have an excess supply of pretty much every single currently produced good or service and an excess supply of labor in the economy if there's a big excess demand for cash, for bonds, for safe assets, for any of these financial things. And then it's the responsibility of the government to try to strategically intervene in financial markets to make sure that even if Say's law is false in theory, it's true in practice, or true enough in practice that we can go forward and keep our market economy running. With that as GDP, what it is and why we're focusing on it, it's time to move on to the introduction to economic growth. First, the second number I want you all to have in your heads right now. That if I want, first of all, you to be able to say that world real GDP today is something like 14,000 times greater than it was at the invention of agriculture, with lots of asterisks about the difficulty or perhaps the silliness of making these calculations. What's the unemployment rate? Yes, 80. Okay, yes. People are converging. Okay. Mm-hmm. A fun thing to do with these clickers is to put up the graph and leave things open, and then see if you can get people to converge in the wrong answer via herd behavior. When this works, this is an absolutely devastatingly powerful point to make during a bubble lecture about how is it that financial markets can grossly overvalue something. In the classroom, it's hard to make it work. Somehow it's easier to get people to converge to the wrong answer when they're actually trading their own money on the stock market than when they're clicking in a classroom. I want the seasonally adjusted answer. I want the 9.4% for the December unemployment rate rather than the 9.1%, which was the seasonally unadjusted answer. The actual unemployment rate that the current population survey interviewers reported, because we do know that Christmas comes every year, and a lot of people are hired to work retail near Christmas and also to staff all the extra UPS trucks. And so we know that during the survey week, during the second week of the month of December, that about an extra 3/10 proportion of the labor force will be at work simply because it's the Christmas season. Okay. So now for the next couple weeks, we're going to kind of drop the business cycle stuff, drop the unemployment stuff. Come back to it in 2.5 weeks from now. But we're going to assume for the next couple of weeks that Say's law works, that at least it works right now, or at least the central bank and the Treasury make it work well enough in practice, even though it's false in theory. And we're going to say, suppose we don't have to worry about problems of there not being enough demand out there in the economy for people to have the money to buy the things that are being made and that people are trying to sell. Suppose you don't have any demand problems. Then what determines an economy's level of real GDP? And we're going to call that real GDP now and for the rest of the course by this big symbol, capital Y. Supposedly Y stands for income, because income is about going to be the same as production by the circular flow principle, and they couldn't use I for income because they were already using I for investment. Doesn't seem to me to be an especially well thought out system of notation. Nevertheless, it's the one we have. Y stands for income. And we're going to be focusing for the next 2 weeks on 3 big questions. Why is the world so much richer, and why are countries so much richer today than they were 50 or 100 years ago? And what are our prospects for increasing riches in the future? And also, why is the world today so unequal as we look across countries? As I said last time, I think I said this last time, I do answer this phone once from any number I don't recognize, which means that there are 2 billion people in the world who could call me if they think I had something to say that would help them understand how to become richer or how to live their lives, and yet remarkably few people do, in spite of the fact that there are an enormous number of people here in Berkeley and elsewhere on the worldwide communications net who will answer your questions. And in any event, even if you have an engineering degree from a middle-ranking engineering university, there are enough books out there to give you access to at least all of human technology up to a generation ago, back when we were maybe 25% poorer than we are now. The world's remarkably close in communication and in trade, and yet it's also almost the most unequal world we've ever seen in terms of income and productivity levels. And we're going to think about these questions by doing something that economists tend to do, which is to start with an incredibly complicated issue and ruthlessly simplify it down to 2 or 3 or sometimes 1 important aspect of it. To simply throw almost all of the real-world complications away to focus like a laser on a very small set of important factors, and then to try to write down a simple model, usually a mathematical model, a simple system that will allow you to understand how these different important factors interact and produce the results we see in the world. The idea is we make an intellectual bet that we're going to write down a grossly oversimplified model of the world, and we're going to find an exact solution to it, and we're going to hope that our exact solution to this grossly oversimplified model world will carry information about how the complicated real world behaves. And this is inherently a dialectical process. We might write down the wrong model. We might get our conclusions and say, that makes no sense, we need to go back and adjust it. We might take a look at the conclusions of the model and at the world and might say, are we misunderstanding the world? Maybe the model has something else to tell us that we hadn't previously recognized. It's a dynamic process. We economists think it's a very useful process. There are other people elsewhere in the university, they're usually called sociologists and historians, who don't think it's a terribly useful process. And right now, political scientists are undergoing an interdisciplinary struggle and crisis of conscience over whether this is a useful process or not, whether it aids understanding or whether it reduces it. But we're economists, and this is what we do. So I'm going to try to write down a model of the determinants of real GDP Y, and I'm going to be looking at a full employment or a normal employment case in which we don't have to worry about any significant shortages of demand in the economy. And I'm going to simply assert that then the level of real GDP Y, and also the level of real GDP per worker in the economy, Y over L, Y real GDP divided by the labor force L, that's going to be determined by technology, including organization, by how efficiently we use our labor in this economy, given the technology that we know and also the things about organization that we've built up over the past 10 centuries, about how to run organizations, and resources. And right now we're just going to talk about labor and capital. Hands and brains on the one hand, machines that we've built to make our hands and brains more effective on the other, and then structures to keep the rain off the machines so things don't rust. Later on, we're going to want to add in natural resources as well. But at the moment, let's just do technology and organization on the one hand, and resources defined as labor and capital on the other. And we're also going to be talking about cumulative processes, about processes of compound growth. Situations in which the economy grows by, say, 3% in 1 year, and then, because it's on its balanced growth path, and because new technologies are being discovered, and because new buildings are being built and new machines are getting installed, it can then turn around and do the same growth thing again in the next year. So we have cumulative processes that build on each other. And here, refreshing a little arithmetic in your minds is, I think, useful. Suppose we have a process growing at 1% per year. How long does whatever's growing at 1% per year take to double? No, not 1%. Let's do 4%. Suppose we have a process growing at 4% per year. How long does some quantity that's growing at 4% per year take to double? Okay. All right, we're coming in on the wire. We have 7 more seconds to put your guess. 2, 1. Display. 18 years. 18 years is the right answer. 25 years, it would have sense if it wasn't compounding. If it wasn't the fact that the economy is larger in 10 years than it is now, means that the same rate of growth in 10 years will actually add more in GDP than 4% growth adds to GDP now. Answer E is a reasonably honorable one, at least. B and D are things that are hard to get as answers out to this particular question, unless you say, well, it's got to be less than 25 years, but I'm not quite sure how much. Let's work through this. Let's multiply it out. We start with our quantity at 1. After a year, it's at 1.04. After 4 years, it's almost at 1.17. Why is it nearly at 1.17 after 4 years rather than 1.16? Well, because it's bigger in years 2 and 3 than it was at year 0. Applying the same 4% growth rate to years 2 and 3 produces a greater increment than the 0.04 increment we got in moving from year 0 to year 1. We can then continue to multiply it out, and we see that after 17 years, we're at 1.947, and after 18, we cross 2. We're at 2.0258. While if we were just adding 0.04 to our quantity for each of those 18 years, we'd be 1.72. So the compound interest matters. The compound interest matters because it adds almost half again to the amount of growth. It adds, say 30 to the 72 worth of growth that you'd have had otherwise. That's why we go through this, because even in relatively short periods of time, when you have a cumulative compounding process, the fact that it's compounding matters. All right, suppose we have 6% per year instead of 4% per year for our growth rate. How long will something growing at 6% per year take to double? Will it be slightly different numbers this time? Will it be 18? Will it be 12? Will it be 6? Will it be 50? Or do you want to give up and say it's too complicated to do in your head under these particular conditions? That is B, 12. Okay, B's excellent. B's good. 12 is right, and we don't need to multiply it out, but we do need to notice something. We were talking about a doubling, an increase by 100%. We had a 4% and a 6% growth rate. A 4% growth rate doubled in 18 years. A 6% growth rate doubled in 12 years. What you do is you take 72, you divide it by the growth rate in percent per year. That's how long it takes to double, roughly and approximately. That's the rule of 72. 3 things to notice about the rule of 72. First, it works for having to. After all, a quantity shrinking at 4 by 4% per year will have itself after 18 years. Second, it's only approximate. It's not exact. Third, I want you to have it drilled into your heads. Right? That is, I want you to leave this course being able to say that a quantity growing at X% will double in 72 divided by X years. That's a genuinely useful life skill to have, not that it makes you popular at parties, but it allows you to get a quantitative handle on a lot of processes that you'll have a hard time figuring out otherwise. I once made myself unpleasant in 9th grade math by asking if it was possible that the rule of 72 could be false. If there could be a possible world and a possible system of mathematics in which it wasn't true. I think the answer was no, that this is something that is inscribed in the nature not just of our realities, but of all possible realities. So a little bit more complicated. Suppose we have a process growing at 4% per year. How long is it going to take it to octuple? How long is it going to take until it's 8 times as big as it started out as? Okay, closing in on the wire. Bingo. Okay, yep, C is the right answer. You have a good plurality at C. The way to think about it is if it's an octuple, if it's an octupling, that means it's doubling 3 times. It doubles, and then it doubles, and then it doubles again. That gets you from 1 to 2 to 4 to 8. Doubling 3 times, each doubling takes 18 years. An octupling will take 54 years, will take the time of 3 doublings. That's what I want you to know about compound interest and about cumulative process. Now let's turn to the basics of our model. As we said, we were going to worry about real GDP Y and its determinants. And its determinants were going to be resources and technology. And for resources, we'll think about the labor force, which we'll call L, and the capital stock of machines and buildings in the economy, which we'll call K for capital. Why not C? Because we'd already decided to use C for consumption when we got to this. And at least capital begins with the letter K in German. So that's something. It's not a great notation system, but we're stuck with it. And for the efficiency of labor, we're going to use the letter capital E, E for efficiency. And we're going to start with a production function. We're going to write down a simple algebraic mathematical rule relating what the real GDP of an economy is going to be as a function of its capital stock, of the efficiency of labor, of the labor force, and also of this little Greek alpha thing, this script A, which is going to tell us something about the relationship between capital accumulation on the one hand and increasing productive potential on the other. We're also going to want to think a lot about the capital output ratio in the economy. That is, take the value of all of the machines and buildings, of all the capital in the economy, and divide it by a year's GDP. And so the capital output ratio, K over Y, we'll write that by this little script lowercase k that's actually a Greek lowercase kappa on your keyboards. We're going to think a bunch about the determinants of that kappa as a way of getting to what the level of output is going to be. So why this function? Why write down this rule that y equals the k to the alpha times paren el close paren to the 1 minus alpha? Or more English, that an economy's level of real GDP can be determined by taking its capital stock and then raising its capital stock to the algebraic power of some number alpha between 0 and 1, and then multiplying that by the product of the efficiency of labor and the size of the labor force in the economy, also raised to an exponential power, but in this case the power 1 minus alpha. It's not the case that there's an enormous machine buried somewhere in the earth called the production function that determines what the level of production in an economy is going to be. You know, like one of those science fiction novels in which the machine takes over people's brains and it calculates what they're going to do, and so it makes them perform the amount of work that produces that amount of final output. No, instead people have work with their machines and their buildings, and they make stuff and they sell stuff and they trade stuff and they buy intermediate goods and they sell intermediate products, and the whole thing adds up, and you have your final sales, and that's the GDPY that's measured, and the Bureau of Labor Statistics counts the labor force, and the census of manufacturers and other censuses try to count the capital stock. And it all adds up in a huge mishmash of 150 million workers, 10 million firms, uncountable items of technology, uncountable numbers of capital, $14.2 trillion of GDP. Why are we pretending that we're going to analyze the economy as if there's this gigantic algebraic machine sitting under the earth somewhere, and we simply feed it 4 numbers, and it cranks for a while and comes out with a number for real GDP? Well, we want to write down this algebraic relationship because we hope it's going to be a reasonable approximation to how the real world works in a certain sense. In what sense? Well, we think that if we were going to double the labor and capital in America, we'd probably double the level of real GDP. That for every factory before, we'd have 2 factories after. For every worker before, we'd have 2 workers afterwards. Twice the number of workers working with twice as many machines in twice as many buildings. It's hard to see why that wouldn't produce twice as much output. So if we're going to write down a very simple rule to kind of tell us how production varies with the resources the economy has, it better be one in which if we double resources, we double production. And this algebraic function has that property. We also would like it to have diminishing returns. That is, oh boy, back in the 1950s, I think it was IBM President Thomas Watson said that he thought there might be a demand for 5 computers in the world. One of them would be for the United States' air defense system. One of them would be for the Soviet Union's air defense system. There'd be another one that the Census Bureau would need to do its calculations. Maybe the biggest insurance companies would want to have one. That's how he got up to 5. Everything else, he said, nah, paper and pencil and mechanical calculators should be enough. But the computers that were in use then were all extraordinarily valuable. People really, really loved them. They were scheduled within an inch of your life. Even in the mid-1980s, back before most of you were born, when I was working with computers, the time of the computers was so scarce that we economics graduate students were only allowed on after 5 p.m., after the more high-priority users had gone home. And furthermore, unless our programs were absolutely perfect, it was simply not worth the time of the central processing unit to spend any time running it. So we would take our large decks of punched cards, one after the other, over to the computer lab, and we would feed them into the computer card reader. And almost all of the time, what would come back would be that the preprocessors saw your program and it was incoherent. Job control language error in statement 6. Go back and punch another card and swap in the good card for the incoherent card, and then we'll let you submit it again in another 2 or 3 hours when the job's submitted by people who understand how to do computer syntax actually run. This meant that being a research assistant for an economics professor in the mid-1980s was an extremely cushy job, because you would basically work for maybe 5 minutes an hour trying to fix your programming errors. And then you have to wait for 55 minutes for the job to come back and tell you what your errors were. Right now I have 1, 2, this has 2, 4, this has a 5th, this has 2 more. Right now, I'm using 7 microprocessors, each of which is more powerful than all the computers in the world were in 1955. Yet, the value produced by the computers in the world in 1955 far exceeded the value of my 7 microprocessors, which are at the moment doing nothing other than substituting for this particular transparency projector, and letting me put a slide up on the screen. If you have more capital in the economy, if you double the amount of capital in the economy without doubling the amount of labor, you do not expect to double the amount of output. Instead, output is going to go up by some smaller amount. So you'd like to have a rule for describing how production relates to resources, by which if you increase the economy's capital stock by 1%, you don't increase production by 1%. You increase production by something less than 1%. By how much do you increase production? Well, that's what this letter alpha is supposed to tell you. Alpha is going to be some number. Alpha is going to tell you how quickly these diminishing returns to investment and capital accumulation set in. If alpha is small, if alpha is near 0, then you increase the capital stock and you don't increase production by very much. Diminishing returns set in immediately. If alpha is almost 1, well, you increase the capital stock by 1% and production increases by almost 1%. Diminishing returns take a long time to set in. The reason we like to write down this particular function is it allows us to tune itself across a number of different economies. Have an economy in which diminishing returns set in quickly, then you can use this equation and just say that alpha is going to be something small near 0. Have an economy in which returns aren't diminishing very quickly at all, well then use this equation and say that alpha is close to 1. So we insist that we want to double labor and capital and you're going to double production. We insist that if you want a model that will tell us if you increase the economy's capital stock by k%, you're going to increase output by some lesser number, by alpha percent. And you also want to say that if the labor force is constant in the economy, and if the capital output ratio is constant, if you're kind of saving the same proportion of output so that output bears the same relationship to capital as it used to, and if the efficiency of labor grows by 1%, then you'd like output and the capital stock to grow by 1% as well. You'd like that to be true, and that's largely a matter of definition. That is, if the capital stock grows by 1% and the efficiency of labor grows by 1%, you really would want output to grow by 1% too, and if it doesn't, then you have the wrong definition for how efficiently you're using your labor. Those three things, constant returns to scale, diminishing returns to investment in capital, and this definitional thing that the efficiency of labor in this equation should actually measure the efficiency with which labor is used to produce things. Those three things nail this function down. This is the only rule that you can write down relating labor, capital, the efficiency of labor, and this diminishing returns parameter alpha, and get output out as a result. So we really don't have much of a choice if we want all of those things to apply, and also get an equation that's extremely easy to use for what-ifs, and also give you an equation that's flexible. So from now on, we're going to ruthlessly simplify all of our 150 million workers and our 10 million firms and so forth down and simply say that the market economy is going to take the labor, the capital, the efficiency through the technology, through efficiency of labor that we throw at it, and it's going to tell us what the level of real GDP is. It's going to be y determined by this equation. So that's the first part of our model. It's going to be this production function. The second part of our model is going to say that we're going to want to study economies that are in some sort of balanced growth. That we're not going to be terribly interested in situations in which the capital stock in an economy is growing much faster than production, or in which the capital stock is growing much slower than production. Why not? Well, because such situations are unstable and transitory. That, after all, if the economy is saving a large share of its output, then the capital stock K will be growing faster than output, and the capital output ratio will rise. And as the capital output ratio rises, diminishing returns will set in, and each additional unit of capital is not as productive. And so our ability to keep the capital stock from growing as fast will slow down. And eventually, the economy will converge to a point at which it's saving just the right amount, where the capital stock and the output level will be growing at the same rate, and thus our little script k, our capital output ratio will be constant, and growth will be balanced. And this is another thing that economists do. The world is complicated and tends to be out of anything you might call of economic equilibrium at any point in time. But in general, the world is heading for, the economy is heading for some particular equilibrium configuration. And if the economy gets to that equilibrium configuration, it's going to stay there until something else happens to disturb it and shock it and knock it away. And it's a lot easier to analyze equilibrium configurations than dynamic disequilibrium ones. So we're going to focus first, and I think last too, on balanced growth equilibriums. Say that there was a time in the past when the economy was out of equilibrium, its growth equilibrium, when capital and output were growing at different rates. And maybe I'll make you do one of those on the second problem set. But for the most part, we're going to say we want to assume that whatever process has pushed the economy toward its equilibrium configuration has come to an end. And we just have to worry about situations in which the capital-output ratio is constant, in which the economy's capital stock and its level of output are growing at the same rate. And then what is just the right amount when we say the economy has to be saving just the right share of production? Well, it's easy to figure out. The textbook goes through this in exhausting detail. In a way, it's simply a property of our particular production function. That after all, if the capital stock K goes up by 1%, then Y goes up by alpha percent. So if the efficiency of labor E goes up by G%, and L goes up by N%, and Y goes up by Y%, then we can write down this y, little y equals alpha little k equation, where little k, lowercase k, is the amount by which the capital stock is going to go up. This is simply an immediate consequence of our writing down this particular production function. And if growth is to be balanced, then y has got to equal k. Little y has got to equal k, that the capital stock and the level of output have to be growing at the same rate. And that equation tell you immediately that the rate of growth of output, little y, is then going to be the rate of population growth, n for number of workers, plus this thing g, and g for growth, the growth rate of the efficiency of labor. So what did I just say that the n in our model is? In this equation, y equals n plus g? No. Immediate retention question? Important from my perspective to figure out how much setup I have to try to give these things for the lectures to be truly worthwhile. Not just for me, right? I seem to get paid whether I lecture well or badly, but more important for you all. Only 46%, the rate at which, the rate of growth of population in the labor force. The rate of growth of the efficiency of labor, that's going to be capital E in this model. The number, or rather the value of capital goods in the economy, that's going to be capital K in our economy. The share of GDP that's saved and invested that is devoted not to consumption either by the government or by households, but instead to saved and invested to add to the economy's capital stock, that's going to be S. The steady state level of population, that's in one of Thomas Robert Malthus's models of stagnation and despair. We aren't going to be doing that, at least not right now. Right now, N in our model is the rate of growth of the population and the labor force. And the important thing to carry away from reading the textbook is that in balanced growth, the rate of growth Y of the economy, of real GDP in the economy, is going to be equal to the rate of population growth N plus the rate of growth G of the efficiency of labor. Another question as to whether this is getting in or not. When we write our production function, a point of the little script alpha is what? Is it the rate of increase of the efficiency of labor? Is it usually less than 0.5? Is it always greater than 1? Is it the rate of growth of the capital stock? Is it a number that determines how rapidly returns to adding more capital to the economy diminish? Okay, we have 2/3. Yep, okay, people are converging in. That's not fast enough. Yeah, it's the number that tells you how rapidly returns to adding more capital to the economy diminish. That's the function of alpha. If alpha is small, near 0, then there's really not that much point in trying to tune the economy to save and invest more. If alpha is large near 1, then there's a lot of point to saying we should be saving and investing and accumulating more and adding more to our capital stock. Although I dare say with at least some kinds of capital equipment, we seem to have reached near satiation. That is, I can't figure out how having an 8th working microprocessor at my disposal right now would raise my productivity at all. Except maybe if this thing had another core, it could do a better job of indexing the hard disk. But that's extremely low value. Now, let's skip this one. We've already asked more than enough. Okay, so we had our steady state balanced growth equation. We said that if growth was to be balanced, that y, the rate of growth of output, had to equal k, little k, the rate of growth of capital. And so the rate of growth of the capital stock, little k, has to be equal to little y, the rate of growth of output, has to be equal to n, the rate of growth of the labor force, plus g, the rate of growth of the efficiency of labor. But we also want to say something else about the rate of growth of the capital stock. We want to say that every year a fraction delta, this little d with the script tail, this little d with the script tail in there, capital wears out, becomes obsolete, rusts away, breaks, has to be replaced. So that if nothing else were going on, the rate of growth of our capital stock would be negative as the stuff wore out. But we don't just have depreciation. We also have savings and investment. We take a share S of our total GDP and we save and invest it in adding to our capital stock. How much does this savings increase the capital stock? Well, to figure out that, we have to take S and we have to divide it by the capital output ratio, kappa. That if the capital output ratio is very low, then a given share of output saved will produce a huge increase in the capital stock in relative terms. If the capital output ratio is very high, then even a big amount of savings S will produce only a small increase, relatively speaking, in the capital stock. We capture this by dividing the savings rate by the capital output ratio. And so now we have two equations for what the rate of growth of the capital stock has to be if the economy's growth is going to be balanced. On the one hand, we know that the rate of growth of the capital stock is this S over kappa minus delta, this term that comes from the combination of savings to add to the capital stock on the one hand and depreciation to reduce it on the other. On the other hand, we know that output's going to be growing at n plus g, and that the capital stock, if the economy's balanced, has to be growing at the same rate. This gives us S over kappa minus delta equals n plus g. And that tells us that the economy's capital output ratio, well, in order to calculate what the economy's capital output ratio, you simply take its savings rate and you divide it by the sum of three things. Of delta, the rate at which capital stock wears out, the share of capital in the economy that wears out every year. G, the rate of growth of the efficiency of labor as you add more and better technology to your workers' skill sets. And N, the rate of growth of the population in the economy. So now we've managed to nail down, if our economy is balanced, just what its capital intensity will be, of how much capital there'll be for every unit of annual output. And that's an important thing to nail it down, because then we can start calculating what the level of output in the economy is going to be. And we should start with our production function. And since we know what the capital output ratio is going to be, why don't we take the capital stock K and replace it by something that involves the capital output ratio? Well, capital is simply equal to the capital output ratio times the amount of output. That's an identity. You can then distribute the exponent in order to get all of the y and the little kappa terms by themselves. You can then divide in order to get all your y terms on the left. You could then exponentiate to get y by itself on the left. And so you get that output is going to be equal to the efficiency of labor E times the labor force L, and then times this term in front that's missing a parenthesis. There should be two parentheses after the second alpha, but that is the capital intensity of the economy, the capital output ratio, raised to this peculiar power, to this alpha divided by 1 minus alpha power. But we know what the capital output ratio is going to be. We know what the capital intensity of the economy is. That's why we went through all of these calculations here to get the capital output ratio as S over N plus G plus delta. And so we can then simply substitute in for output and for output per worker and get nice little relatively simple expressions for how output and output per worker depend on the efficiency of labor, on this alpha diminishing returns stuff, and on our 4 behavioral variables, on the depreciation rate delta, on the growth rate of technology G, on the population growth rate N, and on the share of production S that is being saved and invested, which means we can calculate where the economy is likely to be and also how changes in any of these things are likely to affect the overall level of prosperity. This is, as I said, interesting because if an economy is not on its balanced growth path, it's heading for there, and it will get there relatively quickly, at least in the 10 millennia historical span. It will get there in a couple of generations, in no more than a couple of generations. So now we can do a bunch of calculations about where the economy is and is likely to be over time. We can take our numbers for what the S, N, G, delta, and alpha and E are at any one point in time, and that'll tell us the level of output per capita. And we also know how most of these quantities are behaving over time. We know that the labor force is growing at a constant rate N, which means that if we want to pick some year 0 and we know what the labor force is in that year, call that L sub 0, we can then just multiply that by 1 plus N T times to get what the labor force is up at year T. This is a handy bunch of formulas to have around, and problem set 2 is going to be applying them. How helpful is this model going to be in understanding the real world? As we've done a bunch of algebra very quickly, and we've made a bunch of absolutely heroic and unrealistic assumptions, have they produced anything that's worth anything at all, right? It certainly won't get you onto the BART without a valid BART ticket, but is it useful for any other reason? Well, take a look up at the formula at the top, right, for output per worker in year T. Well, at first there's going to be this term that I said was capital intensity, this S divided by N plus G plus delta raised to this power. That comes from the balance between savings on the one hand and savings requirements on the other that tells us how capital intensive the economy is. Then there's the level of the efficiency of labor back at year 0, whenever you started analyzing your economy. But since the efficiency of labor is growing at rate G, we know that we simply multiply that E0 by 1 plus G raised to the T power. That's going to tell us what our economy's output per worker level is. And note the N in the denominator here. That's the population growth rate. That tells us that if N is bigger, if the economy has a faster population growth rate, well, then it's going to have a lower capital intensity and it's going to be a poorer economy. Why is it going to be a poorer economy? Well, because of all the savings and investment done in the economy, not as much can be used up to build up the stock of machines and buildings that multiply the productivity of any one worker, but rather a greater share of savings and investment have to be devoted to building up new factories, new machines, and new buildings in order to provide employment for all the extra workers who are associated with rapid productivity growth. So other things equal, a country with faster population growth is likely to be poorer. Now there is reverse causation here. Not just the case that a country with fast population growth is poor, it's also the case that a country that's poor has relatively fast population growth. That in general a country has to be rich enough that women learn to read and have options to work outside the home on a large scale before the population growth rate drops from its pre-industrial to its modern kind of level. If a country's poor, it's unlikely to have a literate adult female population, and unlikely for women to have many options to work outside the home. But even so, even allowing for reverse causation, it's pretty impressive what the relationship is between population growth on the one hand and income per capita, which is about the same thing as income per worker on the other. This being from the gapminder.org website, this from 2004, all the way from the United States, smack here, Japan, smack here, China, smack here, and this is what China's children per woman was exactly in 2004. If you look at what the population growth rate of China had been over the preceding 60 years and what the average children per woman had been over the preceding 70 or 80 years, it is up here. The fact that China's down here means it's in rapid transit to a lower population growth equilibrium, in large part as a result of the relatively stringent one-child policy. India, which didn't have a one-child policy, is not that far behind China in terms of falling fertility. And up at the far left, with still extremely high rates of population growth and fertility and extremely poor, you have Africa, the dark blue, with South Africa kind of here, about halfway between the richest of the rest of Africa and Europe. And what is this green thing? I bet you the green thing is Papua New Guinea. Well, I need to look up what the green thing is. And since I haven't set up my internet connection, I can't do it on the fly. So, this model tells you something useful about the relationship between population growth and prosperity, even taking account of the fact that there's a bunch of reverse causation. How helpful is this model? Well, once again, back to our old equation up at the top, right? S equal Y over L equals this savings rate divided by N plus G plus delta raised to this power times the efficiency of labor. And this time, let's notice the S in the numerator. A country that's saving and investing more is going to have a higher capital intensity, is going to have more capital goods per worker, and so its workers are going to be more productive even if they're working with the same efficiency simply because of the greater capital intensity. So other things equal, a country with a higher savings investment share will be richer. And there is reverse causation here as well. That is, a richer country, well, a rich country is one that's very good at making machines. That's one of the reasons that you're rich. And most capital equipment is machines. And so if you're good at making machines, then machines will be relatively cheap, so it'll be easier to devote a lot of your energy to investment. If so doing, you can do so cheaply. So there is reverse causation here. It's not just the case that countries with higher savings rates are richer. It's also the countries that are richer for other reasons have higher savings rates. Nevertheless, once again, you can see the pattern, although the pattern is not as strong as it was in population. You have some extraordinary outliers, like Botswana, as it stood in 1980. a very large share of investment in machinery and equipment in Botswana, and yet extraordinarily poor. Anyone want to predict where Botswana is now? In spite of the AIDS epidemic, Botswana's kind of close to tripled its relative income as a share of U.S. Since then, in spite of having something like a fifth of its adults now HIV positive. Of course, embarrassing are Tanzania, Zambia, and Zimbabwe, which also had extremely high investment rates and have done extraordinarily poorly over the past 25 years. I would argue because those economies made much too heavy a bet on central planning by the government as an economic development strategy. When you're hiring your development advisors from North Korea and they're advising you on your industrial structure, it's not likely to turn out well. Especially if, like Robert Mugabe in Zimbabwe, you also bring in people from North Korea to advise you on democracy and on how to control the people. But nevertheless, there is a relationship there. And I would argue, or at least Larry Summers and I argued in a paper we wrote in the early 1990s, that if you kind of clean the relationship between prosperity on the one hand and investment on the other, of a whole bunch of other factors also influencing things that didn't make us into our very simple model, you get a much, much stronger relationship. That is, that the fact that this particular scatter is not a terribly impressive one is because there are a bunch of factors that are important for growth but that don't make it into our simple model. And once we clean the model of those factors, well, we then have a much better picture, except that something's going wrong with Costa Rica. Costa Rica ought to be much richer than it is. And something's going wrong with Finland. And something's going very right with Hong Kong. We think what was going right with Hong Kong was that in 1985, when we actually took the snapshot of how prosperous it was collecting enormous rents for being virtually the only open window into the Chinese economy. That even though this was 7 years after the start of Deng Xiaoping's reforms, you still, if you wanted access to China's production and China's market and China's labor, you had to go in through Hong Kong. And Hong Kong managed to profit enormously from that. Costa Rica, we never found a terribly good explanation for, nor Peru. Finland, the problem was it was so tightly coupled to the economy of the Soviet Union, and the economy of the Soviet Union had had an absolutely horrible 10 years before 1985. So we could attribute it to that. We were happy. This convinced us, at least, that this economic growth model had a good deal to contribute. Now let's ask how this lecture's gone. Been trying to do an awful lot, and trying to do an awful lot quickly, on the grounds that it's useful to go over this stuff once verbally, but I at least find I really have to learn this stuff from the textbook, or it doesn't stick, and I want to get on to stuff, to actually using the model, because that's what it's for. I don't want you to remember the derivation. I want you to be able to use this to make calculations and assess situations. Oh dear. No two slows. I guess the plurality has to rule. Too fast. Okay, next time I go through a model like this, I'll try to go through more slowly and more coherently. But what I'm going to want you to get out of this is not how I derived these conclusions. For that, you can always go back to the textbook if you want to derive them. I want you to get out the particular rules of thumb. And the most important rule of thumb is this growth equation here. So let's see if you can apply it. Let's suppose that our savings rate is 20% of GDP is 0.2. Let's suppose that our population growth rate is 0.01, is 1% per year. let's suppose that our efficiency of labor growth rate is 2% per year, 0.02. Give us a depreciation rate of 0.02 and an alpha of 0.5. What then is y over L going to be in this particular economy? It's very hard to do, especially if you haven't done it before. The right way to do it is to note that if you add up ng and delta, you get 0.05. And if s is 0.2, then 0.2 divided by 0.05 is simply 4. And if you notice that if alpha is 1/2, then alpha divided by 1 minus alpha is simply 1. So that all of this first bunch of stuff in here, this is simply 4 raised to the first power. And with E at 10,000 per year, we get 40,000 per year. Okay. I'm tempted to give credit for E, but I'll give people credit for A as well, since that's the right answer. Well, let's try another one. Let's keep the efficiency of labor at 10,000 per year, but let the savings share go up to 27%, and let's lower a couple of other things. What then is the economy's level of output per worker likely to be? Tricky part of this is seeing that if alpha is 1/3, then 1 minus alpha is going to be 2/3, and that 1/3 divided by 2/3 is 1/2. And to remember that if you're raising something to the 1/2 power, you're simply taking its square root. So what we're going to have here is we're going to have 0.27 over 0.03, that's 9. And then we're going to be taking the square root of 9, that's 3. And then we're going to be multiplying 3 by 10,000. And that's going to give us, oh, excellent. That's going to give us 30,000. Oh, that's good. That gives me a great deal of hope for how people are going to do on problem set 2. Let me finish. Simply by going back to the second number that I want you to have drummed into your heads. You got it yet? How much is the unemployment rate out there today? Yep. Okay, you nailed it. Congratulations. Next time, we'll apply our growth model to try to understand what's going on in the world today and what has been going on over the past 2 centuries.